Hello everyone, this is Vishu Chaudhary, and today I will provide you the detailed solution of JEE Main 2024 1st February Shift 2 chemistry paper. So let us see the paper. Here is the question number 1. The transition metal having highest third ionization enthalpy is, we have 4 options: chromium, manganese, vanadium, and iron. Let us write their electronic configuration. Chromium is argon, 3d5 4s1. Then we have manganese, which is argon, 3d5 4s2. Then we have vanadium, which is argon, 3d3 4s2. And finally we have iron, which is argon, 3d6 4s2. Now the third ionization enthalpy means the third electron to be removed. Now after the removal of 2 electrons, what do we have? Chromium 2 plus is 3d4, manganese 2 plus is d5, 3d5, vanadium 2 plus is 3d3, and iron 2 plus is 3d6. Now we are supposed to remove 1 electron. Now if we see manganese 2 plus is having exactly half filled d orbital. So that means it is this configuration is stable. Now removing an electron from this stable configuration would require a lot of energy. So the third ionization enthalpy for manganese is the highest among chromium, manganese, vanadium, and iron for this obvious reason. Why? Because the half-filled orbitals are, they are as stable as fully filled orbitals, right? So let us discuss the next question. So the answer to this particular question is manganese, right? The next question. Given below are 2 statements. A pi bonding molecular orbital has lower electron density above and below the internuclear axis. And the statement number 2 is the pi star anti-bonding molecular orbital has a node between the nuclei. Let us see. So suppose this is my internuclear axis. This is my, for say, px of 1, combines with the px of another, and they are combining in phase, right? So what type of molecular orbital do we get? We get, here's the nuclei of one, here's the nuclei of another, and we have 2 loops, yes, representing the electron density above and below the internuclear axis, right? Let's suppose that is the internuclear axis. So this is the internuclear axis, which is passing through the nuclei, and we have the electron density above and below this internuclear axis. But in statement number 1, it is saying that it has lower electron density. No, it has the highest electron density above and below this internuclear axis. Now the same px orbital, when they combine out of phase, right? When they combine, we know that they are unjarred, they are unsymmetrical. So when they combine, out of phase, what do we get? This is the nuclei. Right? This type of molecular orbital. Now, if we see, we have 2 nodal planes over here. One is this, and right, one is this, and another is this. So we have 2 nodal planes over here, and if we see this nodal plane is perpendicular to the nuclei. So the statement number 2 says the pi star anti-bonding molecular orbital has a node between the nuclei. Yes, we have the nodal plane which is passing through in between the nuclei, and it is perpendicular to that internuclear axis. So the second statement is correct, but the first statement, which says that a pi bonding molecular orbital has lower electron density above or below this internuclear axis, this is wrong, right? So statement number 1 is true, but statement number 2 is false. I hope the question is clear to you. Let us move to the next question. Given below are two statements. One is labeled as assertion and the other is labeled as reason. Now, assertion. In aqueous solutions, Cr2 plus is reducing while Mn3 plus is oxidizing in nature. The reason is extra stability to half-filled electronic configuration is observed than in completely filled electronic configuration. So if we see Cr2 plus, which is, argon 3d4, right? Now it is saying that it is reducing in nature. Yes, it is reducing in nature. Why? Because if I consider it reducing, it will be converted to Cr3 plus, where the electronic configuration would be 3d3, and by doing so, we have exactly half-filled T2G orbital. Yes, we have exactly half-filled T2G set, right? So yes, this is, we know that here we have higher CFSC value, right? So yes, this is correct, that Cr2 plus tends to change to Cr3 plus, whereas Mn3 plus, if we see, Mn3 plus is, we have argon 3d4. Now, Mn3 plus tends to change to Mn2 plus. You know why? Because by doing so, it has the electronic configuration of 3d5, where it has exactly half-filled d orbital, which is stable, right? Which is a stable configuration. So it tends to change to Mn2 positive, and hence it is oxidizing in nature because itself it is getting reduced. So yes, statement, this assertion is absolute. This assertion, let's see the reason. The excess stability to half-filled electronic configuration is observed than incompletely filled electronic configuration. This is absolutely correct. Here we have the exactly half-filled T2G having a higher CFSE value. Same goes here. There is a more stability if manganese achieve this electronic configuration of 3d5. So both these are correct, and R is the correct explanation of assertion. So 1 is the right answer. I hope this is clear to you. Let us move to the next question. So match list 1 with the list 2. Here we have a set of reactants, and here we have the products. Let us discuss the A part, phenol. Now we know phenol in the presence of zinc dust, right? What do we end up getting? Phenol in the presence of zinc dust, what we get is benzene, phenol to benzene. Now, phenol in the presence of chloroform and a strong base, this is Riemann-Tiemann reaction, right? One of the most important reactions of phenol. In the presence of CHCl3, it is, the reaction for basically involves a carbene intermediate. In the presence of KOH, what do we end up getting is orthosalicylaldehyde. Then the third reaction is Kolbe-Schmidt reaction. So let us see. We have phenol, carbon dioxide acting as an electrophile over here. In the presence of NaOH, what do we end up getting is orthosalicylic acid. We have orthosalicylic acid. And the last one is your nitration of phenol, but in the presence of concentrated HNO3, which leads to polysubstitution, and we end up getting picric acid, right? This is our picric acid. So let us see. A goes with third. So first and second are eliminated. B goes with 1. So we have got the answer. That is, third is the right answer. I hope this is clear to everyone. Let us move to the next question. Statement number 1, both metal and non-metal exist in P and D block elements. Now, we know that we call them transition metals. Why? Because D block elements, they are metals. So there is no non-metal in D block element. So this is absolutely incorrect. Yes, we have metals and non-metals in P block. Statement number 2, non-metals have higher ionization enthalpy and higher electronegativity than the metals. Yes, Now, regarding electronegativity, it is the characteristic of non-metals. So definitely they are electronegative, just like metals are electropositive. Regarding higher ionization enthalpy, yes, because we find non-metals to the right-hand side of the periodic table. So yes, when we move from left to right across the period, the size decreases, and hence the removal of the electron is difficult, right? Because of more effective nuclear charge. So this one is correct. Statement number 2 is correct. So statement number 1 is false, but statement number 2 is true. So second is the right answer. I hope this question is clear to you. Let us move to the next question. The strongest reducing agent among the following, the strongest reducing agent among the following is, okay, reducing agent, that means, now we can say that the tendency to release H. Now these are the members, or these are the hydrides of group 15. We have NH3, then we have PH3, then we have arsenic hydride, then we have antimony, and finally we have bismuth. So we know down the group what happens. Down the group, the bond enthalpy of these hydrides decreases, or we can say the bond strength decreases. Right? Why? Because it is inversely proportional to bond length. Right? The bond becomes weaker as we go down. In the case of bismuth hydride, this BiH3, the tendency to release H, well, I mean, it has the maximum tendency to release H. Why? Because the bond is the weakest over here. And hence, it is the strongest reducing agent among these hydrides. So we have got BiH3, that is third as the right answer, right? The tendency to release H, the more easily it releases H, the more better the reducing agent it is. All right, let us move to the next question. Which of the following compounds show color due to DD transition? All right, if there's a unpaired electron, that electron in the d orbital that is capable of undergoing DD transition. Let us see. We see potassium dichromate, chromium is in +6 oxidation state, and the configuration is D0. Potassium permanganate, manganese is in +7 oxidation state, again it is D0 system. Potassium chromate, it is in +6 oxidation state, again it is D0. Now there is no unpaired electron in D, there is no electron in D, so it won't undergo DD transition. Yes, we know that they are colored, but the reason is not DD transition, the reason is charge transfer transition, the charge transition, right? So regarding CuSO4, we have cupric ion, Cu2+, the configuration is, argon 3d9 4s2. Sorry, this is copper, so it is Cu2+, so we have 3d9. Now we have one unpaired electron over here, right? So that is capable of undergoing DD transition. So yes, A is the right answer. I hope this is clear to you. Let us move to the next question. The set of meta-directing functional groups from the following sets is, all right. So we have cyanide. Now, we know that this NH2 group exhibits +M. Why? Because of the lone pair of electrons. So this set doesn't contain, it is not having meta-directing, all of them. The second one, again, we have this group. So no. Here we have this group, so we have the lone pair of electrons. It is again +M group, so this is also not the case. NO2, CHO, SO3H, COR, that is ketone. Yes, the third is the right answer. All of them exhibits -R or -M. I hope the question is clear to you. A very simple question. Just on the nature of the groups, whether they are meta-directors or we can say electron withdrawing, the ring deactivators. So third is the right answer. Let us see the next question. Select the compound from the following that will show intramolecular within the same molecule, hydrogen bonding. So H2O and NH3 and ethanol all are capable of undergoing intermolecular hydrogen bonding. That means association of molecules via hydrogen bonding. But this orthonitrophenol, what do we have? So here, we can write it like this, and this is OH, it is capable of undergoing intramolecular hydrogen bonding. So fourth is the right answer. I hope this is clear. And we know that this is, we can, how do we separate in this orthonitrophenol from paranitrophenol? This is intra, that is inter. So intra is steam volatile, and so on and so forth, right? So from there also we can, we can get that here is a intramolecular hydrogen bonding. So let us discuss the next question. Lazane's test is used for the detection of, we can detect nitrogen, we can detect sulfur, we can detect halogens, and we can detect phosphorus, right? So nitrogen, sulfur, phosphorus, halogens, all of them. Fourth is the right answer. So let us see. I hope the question is clear to you. Let us see the next question. Which among the following has highest boiling point? All right. Which among the following has the highest boiling point? Now we know that alcohols, alcohols have higher boiling points. Why? Because they are capable of undergoing intermolecular hydrogen bonding. The molecules are associated via hydrogen bonding, and hence they have higher boiling point. They have higher boiling point than their corresponding carbonyl compounds also, right? Or carbonyl compounds have, lesser boiling point than their corresponding alcohols. Why? Because they are capable of undergoing intermolecular hydrogen bonding, leading to the association of molecules. And hence, that is the reason for their higher boiling point among these. Let us see the next question. In the given reaction, identify A and B. All right, let us see. So this is 4, 5. Okay, so here H2. So we know that alkyne hydrogenation in the presence of palladium carbon, we can say this as in the presence of, Lindlar catalyst, we end up getting cis alkene. So A is definitely, 1, 2, 3, 4, 5, 6. So A is definitely, we have pentan, 1, 2, 3, 4, 5. So 2-pentyne we can say, right? This is definitely 2-pentyne. This is 2-pentyne. And here we have, we have butane, and it is undergoing hydrogenation, but this time in the presence of sodium and liquid ammonia, that is Birch reduction. We know what is the product. We end up getting trans alkene, right? So we get trans-butene. So what is the answer? So A is 2-pentyne and B is trans-2-butene, which is, this is a trans-2-butene. So B is trans-2-butene. I hope the question is clear to you. Let us move to the next question. The number of radial nodes for 3p orbital is, okay. So we know radial nodes. What is the formula? N minus L minus 1, and total nodes, that is N minus 1. These are your total nodes. So radial nodes, N is principal quantum number. For 3p, we have N value 3. L value azimuthal quantum number. For p, we have, it corresponds to 1 and minus 1. So we have 2 minus 1, that is 1 radial node. So 1 is the right answer. Simple question. Okay, let us move to the next question. Match list 1 with list 2. So here we have the polyhalogen compounds, and here is the uses. Here are the uses. You can find it directly from NCERT, right? So polyhalogen compounds, carbon tetrachloride, it is used in the fire extinguishers. So A goes with 3. And we have just one option related to that. So we have got the answer, that is it. But let us see the other option. Methylene dichloride, that is CH2Cl2. What is this? So it is used as paint remover. DDT, we know that it is a non-biodegradable insecticide. And freons, they are refrigerators and in the air conditioners, right? All right. So let us see. A goes with third, B with what? C with fourth. Yes, absolutely correct. Okay. Let us see the next question. The functional group that shows negative resonance effect, that is minus R. Now here we have the lone pair of electrons, here we have the lone pair of electrons, here we have the lone pair of electrons. All are plus R groups or plus M groups, but COH is minus R group, right? Simple question. Let us move to the next question. Okay, we have the two complexes. They are respectively known as, all right. So let us see the first one. Cobalt is in +3 oxidation state, that is argon. And here we have 3+, that means it is 3d6, right? And here we have in the second one, cobalt is again is +3, that is 3d6. Now, 1, 2, 3, 4, 5, and 6. We have S, we have outer P, right? And we have outer D. Now, this ammonia acts as a strong field ligand in the case of cobalt 3+. Remember? So, it leads to the pairing up of these electrons. So, by doing so, we have two empty inner d orbitals, right? And what is the hybridization? That is D2sp3. So D2sp3. So we have utilized the inner d orbital. So it is an inert orbital complex and also called spin paired complex. So the first one is inner orbital. Is it a spin free? No, it is spin paired. So second may be the answer. Third, no, it is not outer orbital complex. We have utilized the inner d. So it is an inner orbital complex. And for this, we know the same scenario, but this time no pairing takes place. So this one is outer orbital complex because we will be taking into consideration the outer d, right? And the hybridization will be sp3d2, and it will be spin-free complex. So let us see. It is a spin paired? No, this is spin free. So we have got the second answer. That is, first one is a spin paired complex, and the second one is a spin free complex. All right, let us move to the next question. Given below are two statements. SiO2 and GeO2 are acidic, while SNO and PbO are amphoteric in nature. We know the oxides of silicon and germanium, they are acidic in nature. CO2 is also acidic in nature. So yes, they are acidic in nature, and SNO and PbO, SNO2, PbO2, all these are amphoteric. This is true. Allotropic forms of carbon are due to the property of catenation, yes, and p-pi d-pi bond formation. P-pi. Now in carbon there is no d orbital, so how can it be p-pi d-pi? Catenation is a property of self-linking, right, via covalent bonds. So where is this D came from? There is no D in carbon. So it should be p-pi p-pi bond. It should be p-pi p-pi bond, not p-pi d-pi. So the first one is correct, but the second one is wrong because of this d-pi. So first is true, second is false, third is the right answer. I hope this is clear. So please, you are suggested to read the question properly. Here lies the answer itself. Okay. Let us see this set of reactions. Let us start with the first is ethyl bromide in the presence of alcoholic KOH. E2 elimination. What do we end up getting is alkene. Then we have addition of bromine, right? We will get vicinal dibromide. We will get vicinal dibromide. Then it is your excess of KCN. Excess of KCN. So substitution reaction, Br negative will be replaced by Cn minus, yes. And finally we have hydrolysis, and it is excess. It is not partial. Partial would have given us, amide, but this is your complete hydrolysis since it is in excess. So what do we end up getting is cyanide. Nitriles are hydrolyzed to acids on complete hydrolysis. Partial hydrolysis gives amide. So we end up getting this. And what is the name of this? This is succinic acid. So this one is succinic acid. I hope the question is clear to you. Let us move to the next question. Solubility of calcium phosphate. All right, we have calcium phosphate. So this is solid, solubility. So what do we have? 3Ca2 plus aqueous plus 2 phosphate 3 negative aqueous. The molecular mass is M. In water is W gram per 100 ml. That means the solubility is given, right? We can find out solubility. Its solubility product is, okay. So we know KSP is, now let us say that the solubility here is S. So the solubility will be 3S and here it will be 2S. What is KSP? It is the product of these raised to their coefficients. So what do we have? 27S3 into 4S square, that is 108S5, right? We are supposed to find out the solubility product. Now, for solubility, like I said, W per 100 ml. So we can write W upon the molecular mass is given to be M and the volume is 100. And since it is in ml, so we can divide it by 1000 and it is whole 5. So when you solve it, the KSP will be 108 into, this is 10 to 10 to the power 5. This is W by M to the power 5. And since, okay, so we need to make it nearly 1. So that will be, if I write it 1.08, that will become 10 to the power 7, W upon M to the power 5. So we can write it approximately 1. So it is 10 to the power 7, W upon M to the power 5. I hope the question is clear to you. Let us move to the next question. Again, the statement type question. Dimethyl glyoxime forms a 6-membered covalent chelate when treated with NiCl2 solution, that means nickel 2 plus, in the presence of NH4OH. And statement number 2 is Persian blue precipitate contains iron both in +2 and +3 oxidation states. All right. So let us see the first one. Yes, we know this nickel DMG complex, right? So how can I write it? We can write it like this, right? Let's say this is O minus, then we have this. This is the complex, let's say O minus. This is stabilized by hydrogen bonding, and then we have nickel 2 plus. So this is the nickel DMG2 complex. DMG whole, this is nickel DMG whole twice complex. Yes. Now, if you see carefully, it is saying that it forms a 6-membered covalent chelate. Now, there are 5-membered, 1, 2, 3, 4, 5. There are 5-membered covalent chelate when treated with NiCl2 solution. So we have the 5-membered, right? Here we have the 5-membered. Because though we have 6-membered ring, if the question comes how many total number of rings, then we have 5-membered and 6-membered both. But dimethyl glyoxime is forming 5-membered chelate rings, right? 5-membered chelate rings. So it is not 6-membered. We are having 5-membered chelate rings, right? And then in statement number 2, Persian blue precipitate contains, Persian blue precipitate contains iron both in +2 and +3. So in the estimation of nitrogen, we get this Fe4, FeCN whole 6 whole 3. This is the Persian blue coloration compound that is formed. And we know that here we have the +3 oxidation, here we have the +2 oxidation, and this is Persian blue. Then there is Turnbull's blue also, where these oxidation states are reversed. So yes, the second statement is absolutely correct. So statement number 1 is false, but statement number 2 is true. I hope the question is clear to you. Let us move to the next question. All right, section B, question number 1. Total number of isomeric compounds, including stereoisomers formed by monochlorination of 2-methylbutane. All right, we have 2-methylbutane, monochlorination. So we can substitute here, 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 and here, 4 different positions. So let us see. I can substitute it here. I can substitute it here. I can substitute it here. and here as well. Okay. So total number of isomers, including stereo. So by if I substitute it here, we have a chiral center. Yes, there is no chiral center, so it will be 1. Here we will have D and L form. No chiral center will contribute 1. We have 2 chiral centers, right? We have 2 chiral centers, so it will be 2. It will be 2, the D and the L form, right? So basically, one is this, and the other will be the mirror image of this, right? Okay, so let us see. So 1, 2, 3, 4, 5, 6. So the answer is 6. I hope the question is clear to you. Let us move to the next question. The following data were obtained during the first order thermal decomposition of a gas A at constant volume. It is the first order thermal decomposition, all right, and the data is given to you. They're asking you the rate constant, okay? They're asking you the rate constant. So let us write here, A of gas gives you P of gas plus C of gas, right? And initial pressure when T is equal to 0, it is your 0.1 atm, and at time is equal to 115 seconds, okay, so it is 0 and 0. Here it will be 0.1 minus x, let's say it is x, it will be 2x, and it will be x. Now the total pressure after 115 seconds is 0.28, that means 0.1 minus x plus 2x minus x plus x gives you 0.28, right? So we have 0.1 plus 2x is 0.28. So 2x will be 0.18 and x will be 0.09. So x is 0.09. So let us find out the k. K is 1 upon t, that is 115. ln of initial, that is 0.1, upon final, that will be 0.1 minus 0.09, right? And when we solve it, we will get 0.002, per second. But we are supposed to give the answer in this form, dash into 10 to the power minus 2. So this will be 2 into 10 to the power minus 2. That means 2 is the answer here. So the rate constant is 2 into 10 to the power minus 2. I hope the question is clear to you. Let us move to the next question. The number of tripeptides formed by 3 different amino acids, using each amino acid once, very simple. We have 3 amino acids, A, B, and C. So tripeptides we are supposed to form. So it can be ABC, it can be, ACB, it can be BAC, and it can be BCA. It can be CAB, and it can be CBA. Only these are the possibilities for a tripeptide to be formed, right? So 6 possibilities. I hope the question is clear to you. Let us move to the next question. Number of compounds which give reaction with Hinsberg reagent. Okay, Hinsberg reagent. So let us see the question. Benzene sulfonyl chloride is the Hinsberg reagent. So we know that 1 degree and 2 degree amines, they give this test, Hinsberg test, and 3 degree doesn't give this test. So let us see. The first one is not even amine, so it won't give the Hinsberg test. This is amide. So this is amide, not amine. This won't give the test. This is primary aromatic amine. Yes, it will give. It is 3 degree. No. It is 2 degree. Yes, it will give. 3 degree again. No. Yes, this one will give. This, yes, it will give. It is 2 degree. It is not even amine. It is pyridine. Yes, it will give primary, and it is your amide. So it won't give. So how many compounds are giving this Hinsberg test? So it is 1, 2, 3, 4, and 5. So the answer is 5. Just remember, 1 degree and 2 degree amines give this test. the amides and the pyridines and the diazonium salts, they do not give this test. All right, let us move to the next question. Mass of ethylene glycol antifreeze to be added to 18.6 kg of water to protect the freezing point at minus 24 degrees Celsius. That means you are given the freezing point of the solution. Dash kg is the answer. Okay, the mass you are supposed to give. So we know that delta TF, ethylene glycol, so I value is 1, right? So it would be Kf into molarity. Now delta TF is, it is the difference of the freezing point of the pure solvent minus the solution. So it will be 0 minus of minus 24. Kf is 1.86 for water, and molarity is given mass, that is you are supposed to find out, upon molar mass, which is 62, right? And the mass of water is 18.6 kg, right? So this is 24 is equal to 1.86 into W upon 62 into 18.6. And when you solve it, I have the answer. Let me tell you. When you solve it, you get 14800 gram. Get 14880 gram. Now you are supposed to give the answer in kilogram, so that will be 14.8 kilogram. 14.88 kilogram, or you can write approximately 15. So the answer is 15 kg. Very simple question, just based upon this formula. All right, let us move to the next question. Following Zeldal's method, 1 gram of organic compound released ammonia. We know that in Zeldal's method, nitrogen is estimated via ammonia. That neutralized 10 ml of 2 molar H2SO4. The percentage of nitrogen in the compound is. Now again, a formula-based question. We know that percentage N in Zeldal's method can be calculated as 1.4 into normality into the volume in ml divided by the given mass of compound. Yes, the given mass of organic compound. So let us see, it is 1.4. Normality is molarity into N factor. N factor for H2SO4 is 2, and 2 is the molarity. So the answer is 2 into 2. Volume in ml is given to be 10 divided by mass of given compound is 1, right? When you solve it, it is 14 into 4, that is 56%. So the answer is 56%. 56. All right, let us move to the next question. The question is, the amount of electricity in coulombs required for the oxidation of 1 mole of water to oxygen. All right, so we know that we can write the equation for the oxidation of water, that is O2 plus H plus and electron, right? So how do we write it? 2. Here we get 4 and 4 electron. So this is the reaction for the oxidation of water to oxygen. Now, so according to this reaction, 4 mole of electricity or 4 F electricity is required to oxidize, but here we are oxidizing 2 moles of water to oxygen. They are asking you 1 mole of water to oxygen. So 1 mole of water to oxygen means that we are talking about 2 mole electron electricity. That means 2 Faraday electricity, and that is 2 into 96500, which is 1319, right? So, and we are supposed to give the answer into 10 to the power 5, so that will be 5. So that is 1.9 into 10 to the power 5, or you can write approximately 2 into 10 to the power 5. So the answer is 2. I hope the question is clear to you. Let us move to the next question. All right. For a certain reaction at 300 Kelvin, K value is given to you, that means equilibrium constant, then delta G naught standard Gibbs free energy for the same reaction is minus dash. Again, a formula based question. We know delta G naught is minus RT ln of K, right? So let us see. This is, or we can change it to log. So this is minus 2.303 into R, which is 8.314. Temperature is 300 Kelvin, and this is log of 10. So this is 1. So we are supposed to just solve it, right? Because log 10 is 1. So upon solving, what do we get? We get 5744 joules, 0.14 joules, right? Joules per mole. But we are supposed to give the answer in kilojoules. So first let us change it to kilojoules. So what it would be? It would be 5.744 kilojoule per mole. And then they are asking you to give the answer in terms of 10 to the power minus 1. So we can write it 57.44 into 10 to the power minus 1, right? So let us give the answer. So it is minus, and yes, we have minus over here, minus 57 into 10 to the power minus 1. All right, kilojoule per mole is the answer. So let us move to the next question. Consider the following redox reaction. We have this redox reaction. The standard reduction potentials are given. Okay. If the equilibrium constant of the above reaction is given as K equilibrium is equal to 10 to the power x, then the value of x is equal to. All right. So we know the Nernst equation, but since this is the case of equilibrium, so we have the E cell according to Nernst equation is 0, right? And what is E naught cell? That is E naught of reduction. So let us see here, this is reducing. So we have 1.51 minus E naught of oxidation. So E naught of oxidation is minus 0.49. We need to take the reduction potentials. So what it is? 1.51 plus 0.49, that is 2, right? So it is 2 volts. Now, okay, so we know the formula that E naught cell is equal to 0.059 upon N into log of K equilibrium. So this is the relationship between E naught cell and K equilibrium. Now E naught cell is 2, this is 0.059 upon N. Now N, for N what do? We have MnO4 minus getting reduced to Mn2 plus, and we have oxalate getting oxidized to CO2, right? So we have plus 4 here, it is plus 3 here, it is plus 4, we can write 2 over here, right? So what do we write? We write 2 electron over here, and it is plus 7 to plus 2, so we write 5 electron. Now balance the electrons, multiplying by 2, multiplying by 5. So what is the value of N? The N comes out to be 10 electrons. So 10 electrons are involved in this redox reaction. So it is upon 10 log of K equilibrium. So log of K equilibrium is found out to be, it will be approximately 398, and K equilibrium will be 10 to the power 398. So they are asking you this X only. So the value of X is 398. I hope the question is clear to you. Let us move to the. So here is the last question. That is 10 ml of gaseous hydrocarbon on combustion gives 40 ml of CO2 gas and 50 ml of water vapor. Total number of carbon and hydrogen atoms in the hydrocarbon is, all right. So we have CXHY, the combustion reaction. We can write like this. It gives you X of CO2 plus Y by 2 of H2O, right? So it is given 10 volume or 10 ml, 10, let us say 10 volume. Now, 1 volume of CXHY gives out X volume of CO2, right? 1 volume gives out X volume. So 10 volume will gives out 10X volume of CO2, and this value is given to be 40. So X comes out to be 4, right? Similarly, 1 volume of CXHY gives out Y by 2 volume of H2O vapors. So 10 volume will give out 10 into Y by 2 volume of water vapors, and this value is given to be 50. So Y comes out to be 10. So they are asking you total number of carbon and hydrogen atoms in the hydrocarbon, that is 4 plus 10, that is 40. So 14 is the right answer. I hope the question is clear to you. Thank you so much.